This is a tool for hull design, and in today's video we will design a hull for our small boat, but will it float? Let's find out. This is third revision of this video, and if you would tell me 2 months ago that YouTube would push me so much out of my comfort zone and that I will need so much time to explain the fundamental basics of hull design, I would look you in total disbelief. This is the tool that I will use for hull design, and first step I want to import my boat sketch that we did in the previous episode and to start from there. But looks like we have an obstacle straight away. The tool doesn't have an option to import pictures. So what are we going to do? To overcome this obstacle we can use Rhino servers. I will open reference line drawing I've used before to create the sketch, and I will scale the sketch to match the reference line drawing. Then I will start creating needed lines. First I will start with a shear line. As you can see, I'm using B-spline curves and I'm really not that precise, and I don't need to be. It's very early stage. Sketch is more a guidance than really something that needs to be followed blindly. When the shear lines are finished, I will start drawing the center line. I will start with the bow stem first, and then I will create the keel shape. After that I will create the deck line, and then I'm going to remove the back image and rotate the projections and prepare them to export them in DXF file. Now when we have a DXF file, I will import that file into the hull tool and start creating new lines. This time I will start with the center plane, so I will have 2 points and a line to make a bow stem, then additionally 3 points and create the keel line. When that is finished, I will transfer into the floor plane and create the shear line in it. When that is finished, I'm going to create one big surface that I will project the shear line onto, and then I can trim that surface and get our surface for the deck. Next step is to create projection lines of the chine, one in the center line plane and the other one in the floor plane. Then one of them will be extruded and the other one will be projected on the extruded surface. That means that we have our chine. Now next step is to create a developable surface for the bottom and for the side, and that's it. We have our hull. But the main question is this hull good enough? Will it float or will it sink? So let's find out that. Every object floats if, according to Archimedes' principle, displaced volume of water by that object is equal to the weight of that object. In our case, that means that volume of our hull that is displacing the water needs to be equal to the weight of our boat. And if you recall, we predict that our boat is 1.3 ton heavy, and our client said that he wants draft of 0.5 meter. So let's check what's happening with 0.5 meter. So now let's take a look at hydrostatic properties of the hull at 0.5 meter draft. And we can see that volume is bigger than 1.3, which means that, yeah, the hull will float on a less draft than 0.5, which makes it okay, but is it really? Because is 1.3 ton the weight that we are looking for? Let's dive deeper into that. In the life of the boat or ship, doesn't matter, there are several conditions that are usual or most occurring. One is lightship, and that's when the boat is really just produced and staying still in the water without anything in it, just like you purchase it brand new and that's it. There is a full condition. That's when it's fully packed with fuel, water, cargo, proviant, food, everything, right? Your stuff, everything. And there are numerous conditions in between. One characteristic condition is a half load. There are also loading conditions connected to departure or arrival, because on arrival there is a little bit of fuel, a little bit of water if you plan your trip to the last bit. So it's quite difficult to predict the condition in which boat will sail. So let's stick with 3 of them for now, and that's lightship, half load and full load, and then we will see which one we will use to design the hull for. Now let's use the most beloved engineering tool, and that's Excel. Let's lay down the spreadsheet where we will name every weight. So lightship, proviant, each person 6 of them according to client wishes, and I will make quantity column so I can easily turn on or off the weights. And we can see that for lightship it's 1.3 ton. If we go to full load it's 1.9 ton, and in between it's 1.65. So is 1.65 ton the most favorable loading condition? Most probably, because client said that he will sail mostly with his wife and kids, which is roughly there. So kind of 3 persons. So let's go further with that. Keep it simple. Make a decision, go forward. So let's check where we are with our hull. Okay, so we see that we are a little bit off and we need to adjust our hull in order to get to required or desired, whatever you like to call it, the displacement, which is 1.6, to be more precise, 1.65 cubic meters at 0.45 meter of draft. I will also check if displacement on 0.5 meter of draft is actually higher than required displacement in a full load condition. And now we are there, but is that all? Is that the milestone that we can say our hull is finished? Not yet. How about the trim of the boat? Let's check that. First, let's define the trim. When the boat is in a trim, that means that it's not sailing on an even keel. And the trim is difference between the draft in the forward and draft in the aft of the boat. And trim can be negative and can be positive, depending is it trimmed to the aft or to the forward part. And we want to make sure that our boat sails on even keel as much as possible. Of course, that's very difficult because we see that loading condition is changing through the life of the boat, so you cannot predict everything. It is what it is. We need to go forward. But let's first unpack why a boat has a trim. Every boat, every ship, every object floating in the water has at least 2 forces acting upon it. One is buoyancy, that is providing the floating force, and the other one is weight, that is trying to sink the object, boat or ship. Those 2 forces need to be in equilibrium, and when they are in equilibrium, the object floats. Now imagine that somebody walks in our small boat and change the position. What's going to happen? Well, the center of gravity is going to shift. In that moment, the boat will start tilting to that side and the center of buoyancy is going to shift until it doesn't reach the same vertical line as the center of gravity. And then it's going to become again in equilibrium. So that's it. That's how the trim works. This means that we need to calculate longitudinal center of gravity for our boat. And then we will check how it will float with that value. So let's open our spreadsheet again and start filling in the positions of the mass, of the weight. And you can see for people it's very easy. We know where the seats are, so you just measure and that's about it. With the boat itself, it's very difficult. We estimated only weight and nothing else. So what are we going to do? It's again an obstacle. We are going to guess. Yes, you heard me right. We are going to guess. I know it's not in engineering practice to guess. We need to calculate. But we are in design stage. We are not in engineering stage. So relax and guess. And don't worry. Human eye has an excellent capability to figure out where the center of area is. So try to guess it. What do you think? Where is the center of gravity in longitudinal direction? So from transom towards forward part of the boat. And press the pause now and type it in the comments below. If you type in around the middle, you were correct. Let's unpack this. Let's analyze it. Look, we have a hull, right? And the bow is more slender than the aft ship. In aft ship, there is more volume, there is more steel, there is more weight. However, we have anchor and for sure there will be some storage compartment in the forward part. There are seats in the forward part and a table, but in the aft there is also a seat with a console where we will have most probably batteries and other stuff. But there is one big item all the way in the aft, and that's engine. So engine will cause that central gravity is slightly tilted to the aft. I know, but even if you set it around middle, you will not going to make a huge mistake. So go with the middle. I'm going to guess now. I will do it in a Rhino because that's where we have it in dimensions, so I can measure it, and you can see it's around 2.4 meter, roughly speaking, from zero. And that's what I'm going to write down in my spreadsheet. Now, when we have filled in our spreadsheet with longitudinal center of gravity, we can get longitudinal center of gravity of whole boat. And if you're interested more about this calculation, let me know in comments below, but the idea was to cover it in one of the next videos. Now we need to check how our boat is going to float with this center of gravity. And if we just go into the part of the tool that is related to this, you can see that you can type in the longitudinal center of gravity. If we type our value, this is how the boat floats. So now we need to adjust our hull in order to get the boat float in an even keel condition. So with a little bit of movement of the points and you can see it's a very iterative process. And that's why I'm not used to use Rhino or any other general 3D tool. That's why I love to use specific tools for hull design. But after a few iterations, we are roughly there and we can check it. And yes, and we can check also other loading conditions to see how we will float in that one and those. And you can see when we have empty ship, we are floating with a little bit of aft trim, which is really good because then the water will drain from the cockpit into the water. And that's it. So this is it. This is our hull. We finally managed to finish it. Now the last bits and pieces are create a transom, trim all the surfaces, because you can see that I created a little bit bigger surfaces for deck and to the aft, and that's it. So this was it. This was our hull in the most simple way. There is more to it, of course. We will do that in the future. This is really fundamental. So now when you want to design your hull, you at least can predict the trim and predict draft that it's going to float on. And there will be no surprises about that. Next episode, we will cover resistance calculations and powering, and you will see that there we will lay down foundation for the next steps in hull design. So now download some of the tools that are available. There are multiple tools for the hull design. I'm not going to say that any of them is a perfect, because they're not. They all have pros and cons. So pick up one. Usually they all have free trials, whatever, and create your own hull. Try it. You see, it's not a rocket science. So just go and design your boat. And that concludes this episode. Don't hesitate to share your thoughts or ask a question. If you enjoyed the video, please hit the like button. If you didn't, hit the thumbs down, and please share your thoughts in the comments so I can improve future content. Don't forget to subscribe, and thank you for watching.